Let me show you a simple DC brushless motor. It's powered by an audio amplifier here in the background. That's a standby power of 1.4 watts. We'll use that later to calculate power consumed. It consists of a permanent magnet for the rotor and basically two coils that are connected to the amp. One of the coils is a generator coil that, when placed in the motor, generates a voltage, as you can see on the scope here, as the motor spins. Let me switch over to the motor coil, and also you can see that the amplifier drives a current into the generator coil. Now when this is placed in the motor will spin, and it's just sort of a feedback loop between the input and output of the amplifier. So let me try to demonstrate another feature of this motor technology. I'm going to start with a simple single-phase motor you saw in the first video. Let me start it up. And now I'm going to add in just additional rotors spinning in the opposite direction. And this being in proximity of the motorized rotor, it's going to continue moving that direction. Let me try to add in a third. The third one now is running synchronized with the all three of them. And let me try to add in a fourth one. So now we've got all four of them spinning in a synchronized fashion, each of them in opposite rotations. But they can also be looped around. Now we form basically a four-way arrangement of all four rotors spinning in unison, one clockwise, counterclockwise, clockwise, counterclockwise. So let me show you another variation of how multiple motors can work together. This looks like a single axis, but in fact there's actually four unique axes that could be rearranged, being perpendicular to each other. So let me start it up. Here we have all four spinning synchronously. There we rotated two of them by 90 degrees, and the remaining two. Now we basically have all four running perpendicular to each other. Now let me show you another feature of this motor that's a little bit counterintuitive. I'll be moving the location of the motor coil, and let's see what happens to the frequency and the power. So first we'll start it up. You can see on the scope the input and output waveforms. The power is about 3 watts. And then as I start moving it further away, you'll see in the waveforms that it's speeding up. Also the power consumption is increased. A little bit further, it speeds up further, power's gone up, and then at some point it starts slowing down again. Although the power increases, you go yet further, power increases, and you slowly start the motor slowing down. To some point I just can't drive it anymore. In the opposite direction, pull it closer, it'll speed up, power starts going down. After some point, it slows back down again. I'll be exploring this with a different apparatus in the following video. So this is another version of the same DC motor. The red coil is the generator coil, and the green coil is the motor coil. And I'll first demonstrate how the position of the motor coil affects the speed. So as I move the motor coil in closer, you can see it actually slowing down, and I bring it further away, it speeds up. In fact, it sort of oscillates at this point. Now the other observation is now if I can move the generator coil perpendicular to that axis, so I push it away, it pulls the motor in. If I pull it towards me, it pushes it away. And now there's an interaction between the two coils. If I just let it go on its own, you can see the generator coil swinging towards you, which causes the motor to kind of go back and forth on the perpendicular axis. And there appears to be some interaction between the magnetic field in the green motor coil that pushes away the generator coil, and in turn the moving generator coil enforces the back and forth motion of the motor coil. I just thought that was an interesting observation. So here's another version of this motor that will harness the circular motion of the motor coil. In this example, there are two generator coils located near a smaller tandem rotor on the top of the shaft, and a larger motor coil located near a larger rotor on the bottom of the shaft. The motor coil is on a two-pulley platform that allow it to pick up some circular motion while the rotor spins independently. Let me start this up. So now you can see that the motor coil is picking up some circular force while the rotor spins independently. Of course, I can actually stop the motor coil. If I bring it close, you can see it slows down. I'm going to speed up further away it goes. And I'll just pick up the circular motion as it interacts. There's actually two magnetic fields, the spinning magnetic field of the rotor and a spinning magnetic field that's generated in the motor coil based on the pickup here of the generator coil. I just thought that was an interesting feature of this motor as well. In this video, I'll be demonstrating the interaction between two or more dynamic or moving magnetic fields, which could be a spinning magnet or electrons moving through a coil. The initial driving force will be provided by this simple motor I showed in an earlier video, and give it a kick start to get it going. Then I'm going to take another magnet mounted on a rotor, which I call a follower, and I'm going to give it a kick start. And now, this follower being in proximity with the motor, they spin at the same speed. Now the barber pole striping I have on these magnets indicate the direction of spin, and on the motor they're moving to the right, indicating a clockwise spin, and on the follower it's moving to the left, indicating a counterclockwise spin. Now if I give the follower a 180 spin, it continues spinning, striping now moving to the right, so now they're both going clockwise. And in addition, now I can take this follower and put it in line with the motor, and it continues to spin, both moving in the same direction. However, now I'll give it another 180 spin, get them back to now where they're spinning in opposite directions. And now if I bring it in line with the motor, you'll see eventually loses synchronization and slows down. And now it starts spinning clockwise to line up with the motor. I got more experiments to follow. So this is a continuation of the previous experiment, and I wanted to show, in addition to running in parallel in the same direction or in the opposite direction, if the follower is rotated by 90 degrees, it'll continue, staying in sync with the motor as well, which I find interesting. And if I do another 90 in the other direction, it still is influenced by the magnetic field of the motor itself, which I found interesting. Now I'll put the follower in the tank of water to allow it to move more freely. And you'll see it will align itself with the motor, but it spins in the opposite direction. If I tilt the motor's axis to the vertical position, the follower tilts as well, so that they both spin in the same direction. So for every movement I make to the motor, the follower responds in a predictable way. And notice at times the attraction is strong enough to completely submerge the follower. In this example, I position the follower so that it spins in the same direction as the motor, and the follower repositions itself so now it spins in the opposite direction. So now I'll stack a second tank on top of the first for a second follower, and it will align itself with the other spinning magnets to form a chain of 3 rotating magnets. And now when I move the motor, the 2 followers respond in kind. So in this experiment, we've got one motor on the left side with a follower next to it. And on the far right, we have another motor spinning at a higher frequency and its own follower. And now, what I've noticed is that the 2 followers run by different motors spinning at different frequencies. When they're brought into proximity, you can't really see it, but I can feel that there's no attraction like there normally would be, and there's actually a bit of a repulsion. So if the spin frequencies are different, they have a different behavior.